Alright, so I think this is recording. Let's take a look at this log equation. We're trying to prepare for an upcoming test over Skill 5 packet, and a big part of that packet is solving equations, log equations, and exponential equations. So here we have a logarithmic equation. Immediately, I should probably mention that it's possible that we could get extraneous solutions when we have a log equation. The domain of a log function is not all real numbers, so therefore I have to be a little bit afraid. I can't take the log of a negative number and I can't take the log of 0. So once we get the values for x, we're going to have to substitute them in and make sure that this x squared minus 5x minus 1 is a positive real number. Alright, so the log is by itself here on the left, and I don't have a property that allows us to distribute. This is not log times this, so we don't distribute a logarithm. So I would call this form a log form, and I want to convert this log form to an exponential form. This base of 7 will have an exponent associated with it, not the variable expression here, but this number 2, because a logarithm equals an exponent. So this is 7 squared, and that equals x squared minus 5x minus 1. So you should have a lot of experience solving quadratic equations. You saw them in Algebra 1, you saw them in Algebra 2, you saw them in geometry, and you've seen them in this class. So to solve this quadratic equation, we know that completing the square will always work, the quadratic formula will always work, and sometimes you can factor it, and when you can factor it, often that's the quicker solution, so students tend to gravitate towards that. Let's zero it. Let's make sure that this is equal to 0 by subtracting 49 from each side. Now, when the leading coefficient is 1, I don't necessarily have to do the x method that I talked about in Algebra 1. The true advantage of the x method is when this leading coefficient is a large composite number. Then that really gives you an organized way to factor this. With a leading coefficient of 1, it's pretty easy. X times x will get you x squared. Well, what two numbers multiplied together will give you negative 50, but at the same time add together to give you a negative 5. So you're looking for two numbers that when multiplied together give you negative 50, but yet when you add these together, you get a negative 5. Since their product is negative, one of these numbers is going to be positive and one's going to be negative. The one that's larger in magnitude is going to be the negative number because the sum is negative. Alright, so think about two numbers that multiply together to give us this negative 50. Well, it probably doesn't take people very long at all to recognize that a negative 10 times a positive 5 multiplies together to give you a negative 10, and a negative 10 plus 5 adds together to give us negative 5. So we found the two numbers pretty easily. Alright, so now you have a theorem that allows you to split this into two equations. This zero coefficient theorem, that if a list of numbers multiplies together to give you 0, then at least one or more numbers in that list must be 0. So since x is a variable, but it's a real number, this x minus 10, it's representing a number, and who knows, it could be the number 0. Or this x plus 5, it could represent that one of these has to be true, or otherwise that product wouldn't be 0. So I claim that either x equals 10 or x equals negative 5. Now, I'm not afraid of negative numbers. I am afraid of taking the log of a negative number. So I need to plug in this 10 and make sure that when we do this arithmetic that we get a positive number. So let's grab my calculator. You can probably do it in your head, but let's 10 squared, 10 times 10, well, I don't need the calculator for that, that's 100, minus, well, 5 times 10 is 50, and then minus 1. Well, hey, that's a positive number. So I know that this solution, if I haven't made a mistake, that solution is not extraneous. All right, it does not cause us to take the log of 0 or the log of a negative number. What about negative 5? If we plug in -5, we've got to square it. -5 times -5 is 25. I don't need a calculator for that. I'm subtracting 5 times the -5. Well, that's going to be positive because the double negative there. And then subtract 1. Hey, we're going to get positive 49 again. Both of these are solutions to this original equation. Neither one of them is extraneous. So, hey, I hope that helps. Let's move on to the next one. So here we don't have an exponential, or we don't have a logarithmic equation. We have an exponential equation. I see a variable as an exponent. Now on the left-hand side, I see a fraction. Well, on the right-hand side, if I make this a fraction, one technique that students seem to like is when you have the claim that one ratio equals another ratio, that equation is called a proportion. And one of their favorite techniques in solving proportions, students like to cross multiply. So let's multiply along this yellow diagonal, and then let's multiply along this orange diagonal. So along this yellow diagonal, we have -1 times 4 minus x minus 3, and 6 times 1. Whenever you take the opposite of a subtraction, that's what -1 is telling you to take the opposite. You can just change the order of this subtraction. Or distribute that -1 through, and you can see the -1 times a positive 4 gets you a -4, and the negative times negative gets you a positive e raised to the x minus 3. So on the left-hand side, I have two terms. The term of interest that has my variables, that first term. So I need to add 4. I need to isolate that term. I need to add 4 to each side of this equation. 6 plus 4 is 10. Well, now I'm kind of stuck. I have a variable as an exponent, but I can't add 3 to both sides and get this x by itself. I can't divide both sides by an e, But what I can do is use my properties of logarithms. What if I took the log of each side? And better yet, if I took the natural log of each side. Natural log is ln of x. But they don't write the base there, but the base is implied. The base is e. So if I take the natural log of the left-hand side, I'm going to write it on the left-hand side, log base e of e to the x minus 3. On the right-hand side, I'm not going to bother with writing it as log base e. I'm just going to write ln of 10, natural log of 10, because this ln and this log base e mean the same thing. The reason I'm emphasizing this e is so that you can see this base, log base e, and this base, e raised to the x minus 3, are the same. This left-hand side is just x minus 3. Well, we've almost got x by itself. All we have to do is add 3 to both sides. So my final answer is 3 plus the natural log of 10. That's my exact answer. If they're telling me to give a decimal approximation to that, maybe they're saying round it to 3 decimals. Go to a calculator. Fix your calculator to round to whatever decimal you want. I'm going to fix it to 3 decimals. And I'm going to have 3 plus the natural log of 10. And it doesn't even care if I close this final parenthesis. It does it internally for me. I often close it just out of habit. 5.303. So this is what they refer to as the exact solution, and this is what they refer to as an approximation, that it's approximate to 3 decimals. Alright, so I hope that helps. Let's look at the next one. Here we have a word problem. Now just because it's a word problem, don't jump in there and have math anxiety. You can do it because basically what we want to do is try to make this word problem look like one of the previous problems. So a 50-gram sample of radioactive iodine decays in such a way that the mass remaining is given by the equation m as a function of t is equal to 50 times e raised to the negative 0.087 times t, where t is measured in days, and m of t, this function notation, is the mass remaining in grams. How many days later will the amount of iodine remaining be 25 grams? That's the first thing they want me to answer. That's a question. I see a question mark. Then they have another question for me. How long until only 1 gram remains? So what do they want us to do? Well, first let's look at the equation. Let's write it down. So the problem says that this equation um, is the mass remaining in grams. So as time goes, and it says it's decaying. So as time passes, this 50 grams starts to decay. Maybe in the first 2 hours, 50 grams decays to 49 grams. Maybe maybe in the next few hours it decays to 40 grams. And it wants us to determine how long will it take for it to decay away to where the mass is 25 grams. So the left-hand side is telling us the amount. Let's think about this function as far as input and output. This function has this equation as a rule. But what I'm interested in is trying to get you to think about what the input and output is telling us. We input a length of time, and that length of time is measured in days. Okay, so at 0 days, at t equals 0, we have 50 grams. And then as time passes, it's going to decay. So the output of this function, what this e to the negative 0.087 is doing, is telling us how much of this mass remains as time passes. So the output of this function is an amount. And that amount is the mass, and that mass is being measured in grams. Okay, so we want to know how many days will it take for us to have the amount of mass that's remaining be 25. All right, that's the idea. So with the equation, we don't know the input. We know that the output is 25. All right, we need to solve this equation for t, for the time in days that it took 50 grams to decay to 25 grams. All right, on the right hand side, I have two factors. The factor of interest has my variable t. I need to get that factor by itself. I need to divide both sides by 50. 50 divided by 50 is 1. 25 divided by 50 reduces to 1/2. And that's where this problem gets its name. This is often referred to as the half-life. We're trying to determine the length of time it takes for half of the material to decay. The original amount was 50, and half of 50 is 25. So no matter what the initial and final amounts are, the left-hand side of your equation on your exponential is going to equal 1/2 when you have a half-life. We need to solve this for t. Well, since this base is e, I'm going to take the natural log of both sides. The natural log of 1/2, and to balance the equation, I'm going to take the natural log of the right-hand side. But some students will have difficulty recognizing that the natural log is base e. So I'm going to rewrite this ln as log base e, because that's what it means for ln is log base e. And that's really going to emphasize to you, hopefully it's really clear now, that this base e with this logarithm and this base e with this exponent, they're the same. So what that means on the right hand side, we just get this negative 0.087t. I have the natural log of 1/2 is equal to this number, negative 0.087 times t. I need to get this t by itself. I need to divide both sides of this equation by this negative decimal number. And this factor divided by that factor is 1. So they cancel. And I have t is equal to the natural log of 1/2 divided by this ugly decimal number, negative 0.087. Let's go to a calculator to figure out how many days it'll take for this material to decay to its half-life, to 25 grams. All right. The natural log 1/2 is the same as 0.5. It's easier to probably key it in for me as 0.5. And then divide it by negative 0.087. So to 3 decimal, if we just call this 8 days, so what if we round this instead of to 3 decimals to 2 decimals? Then you'll see that we have 7.97. All right, let's round it to 1 decimal. I wanted to say 8. I'm stubborn. There's our 8. All right. So that in 8 days, you'll have half the material has decayed and half the material remains. So that 8 days is called its half-life. Now the problem asks us another question. How many days will it take for almost all the material to decay, where the only thing left of the material is just 1 gram? So how many days will it take for this 50 to decay all the way to 1? Well, we solve this equation for t. So we do it in the same way. This factor has my variable. I need to get that by itself. I need to divide both sides by 50, just like I did over here. But 25 over 50 reduced, 1 over 50 is not going to reduce for us. And again, since this base is e, I'm going to choose to take the natural log of both sides, because the natural log is base e. On the right hand side, I'll write it in such a way that really emphasizes that for you. So since this log base e and this e raised this power, these are the same base, that on the right hand side we have this negative 0.087 times t, just like we did before. To get the t by itself, to get this t by itself, I'm dividing both sides by this negative decimal number. So I'm expecting this to take longer, because it took 8 days to decay to 25. It's going to take another close to 8 days probably for it to decay all the way to 1. Well, let's be more exact than guessing. Let's key it in. So if we have the natural log of 1 divided by 50, close that parenthesis, and divide that by this decimal number, and I'm getting 45 days, at least to 1 decimal number. So if you want me to write 0.0 and 0.0, I can. So it took 8 days for half the material to decay away. It took 45 days for 49 grams to decay away, leaving us with only 1 gram. Alright, so let's take a look at this problem. Again, it's a word problem. The velocity of a skydiver in feet per second, t seconds after jumping, is given by this equation. after how many seconds will the velocity be 50 feet per second? So you have some plane, and from this plane, you have people jumping out of this plane, hopefully with parachutes, and the the velocity, how fast they're going, um, t seconds after they've jumped from that plane is given by this equation: 90 minus 90 times the quantity 1 minus negative 0.18, times t. All right. The velocity is the output of this function. So what this function does, you give it the number of seconds that it took after you've jumped from the plane, and like 1 second later, 2 seconds later, or 10 seconds later, the output of this will tell you how fast you're going. Okay, and we know that acceleration due to gravity, that as time passes, this velocity is really going to start increasing. All right. So they want us. They're interested for whatever reason in a velocity of 50 feet per second. That's the left-hand side of this. Well, on the right-hand side, that's our input. This t is time. We want to solve this equation for t. We want to get that t by itself. On the right-hand side, I have two factors. The factor that has my t is this binomial. You know, I need to divide both sides of this equation by 90. 90 divided by 90 is 1. 50 divided by 90 reduces to 5 over 9. So we have this 1 minus e to the negative 0.18t is equal to 5 over 9. Alright, we need to get this term that has our variable by itself. We need to take 1 minus 5/9 e to the negative 0.18t. I'm going to rewrite the number 1 so that it's easy for me to do this subtraction. I'm going to rewrite the number 1 as 9 divided by 9 so that these two fractions have the same denominator. I need a common denominator to add or subtract fractions. So on the left-hand side, these two fractions, I can write this as a single fraction by taking the difference of the numerators, 9 minus 5. The denominator doesn't change. So I've taken that as far as I can go. This is an exponential form. I need to get this variable down as a multiplier so that I can get it by itself. I need to take the natural log of each side. And we've seen that in the previous equations in these problems. So on the left-hand side, I've got the natural log of 4/9. And on the right-hand side, instead of writing ln, I'm going to write it as log base e, so that visually you really see that the idea here of taking the natural log of both sides is because when this base and this base are the same, they undo each other, and we just get this exponent, negative 0.18t. So now it's easy to solve for t by dividing by that decimal number. So I claim that I'll take the natural log of 4 divided by 9 divided by negative 0.18. And this will tell me the number of seconds that it takes after I jump out of that plane to reach a velocity of 50 feet per second. Alright. The natural log of 4 divided by 9 divided by negative 0.18. 4.5. And has units of seconds, right? T seconds after being. So you jump out of that plane, and 4.5 seconds later, you're traveling at 50 feet, 50 feet per second. You're going really fast. All right, so let's see if there's another one. Is there another application problem? Yeah. All right, so let's take a look at it. A lake is stocked with bass. So, hey, this is going to be your new fishing hole. The population of bass in this lake after T years is modeled by this function P, and they could have written it in function notation. P is a function of the years, and it's 10 divided by this 1 minus 4 e to the negative 0.8t. So the left-hand side, the output of this function, the input into this function is years. You plug in at 5 years, 10 years, whatever, and the output of this function will estimate the number of bass that are in the lake. Okay, so it's a count. All right, let's see if we can figure out what's going on here. How many years? They want us to solve for t. It's saying how many years, so that's t equals what? Will it be before the bass population reaches 1,000? So the output of this function, the left-hand side of this, is 1,000. And on the right-hand side, I need to figure out what t is that will cause this output to be 1,000. Right-hand side's a fraction. Let's write the left-hand side as a fraction. We have a ratio, the claim that two proportions are the same. We're going to multiply along one diagonal and also multiply along the other diagonal. And students seem to like this technique of cross-multiplying to solve proportions. So we have 1,000 times this binomial. And on the right-hand side, 1 times 10, hey, that's 10. All right. On the left-hand side, there's two factors. The factor of interest contains my variable. I need to get rid of this 1,000. I'm going to divide both sides by 1,000. 1,000 divided by 1,000 is 1. We say that those cancel. So on the left-hand side, we have 1 minus e raised to the negative 0.8t is equal to, and 10 divided by 1,000 is 0.01. The decimal moves 3 places. 1, 2, 3. You can double check me. And 10 divided by 1,000. Well, if I round it to 1 decimal, 0.01. Alright. I need to get this term that contains my variable by itself. So I'm going to switch places with these. I've got 1 minus 0.01 is equal to e to the negative 0.8t. Well, 1 minus 0.01 is 0.99. I need to take the log of each side now so that my variable that's currently in an exponent will come down where we can do our properties of qualities of adding, subtracting, multiplying, and dividing both sides of the equation to get t by itself. So if I take the natural log of the left-hand side, I have to take the natural log of the right-hand side, but I'm going to write it as log base e. That really emphasizes to you that this base and this base are the same. There, I'm going to continue over here. I have the natural log of 0.99 is equal to, well, this negative 0.8t. Alright, I'm trying to get t by itself, so I divide both sides by this negative 0.8. Negative divided by negatives cancel, and I go to the calculator. I'm starting to get a little bit tired. 0.99 divided by negative 0.8. Let's round that to 3 decimals. Well, 2 decimals. Number of years. So this is saying that not even a year, just a small fraction of a year went by. So most likely I've made a mistake somewhere. Like I say, I was starting to get a little bit tired. Let me pause the video, look at my work, and see if there's a sign error or something gone somewhere. Like if I subtracted, when and did a silly error. So I'm going to pause this. I'll be right back.